Good morning, everyone. We're ready to get started. Welcome to today's presentation, where we're going to talk about how to build reliable applications on GCP with our customers, Cruise and Egnyte. So here's what we're going to cover today. We will start with something called its deployment archetypes. I'll go into a little bit more detail on what that means. Think of it as grounding ourselves in a little bit of theory before we get to the real-world examples, starting with Cruise, followed by Egnyte. And then at the end of the session, we'll take Q&A. We have timed all of our talks. We will have plenty of time for Q&A, so we will take that at the end. So if you have questions, please take a note of them. I promise you we will get to them. Okay? Now, before we dive in, you're probably wondering who we are, so it makes sense to introduce ourselves. And we will start with you, Nitish.
Hi, my name is Nitish. I'm on the container platform team in the infrastructure org at Cruise. I've been with Cruise about 4 years, and great to meet you all.
Roman?
Hello, I'm Roman Kleiner. I'm a VP of Engineering at Egnyte, and I'm responsible for everything to do with Egnyte's platform, including how it runs on GCP.
Lee?
Hey everybody, my name is Lee Gates. I work at Google Cloud studying reliability, availability, and performance, and happy to be here with you today and excited for our talk.
Wonderful. Folks, my name is Tim Isaacs. I lead GCP platform reliability from a product management standpoint, and I'm super excited to be here and lead you through the next 10 or 15 minutes before we move to the other speakers. Wonderful, let's get started. So what are we going to cover today? The key objective here is to discuss a few deployment architectures, what we call deployment archetypes. It's just another way of saying deployment architectures. And then run through those with 2 case studies, one from Cruise, and Nitish will walk us through that, and the other from Egnyte. So what we're trying to do here is start with a little bit of theory and then match that theory with some real-world examples. A quick sidebar, what you see linked below is a link to a very popular paper. It's called Deployment Archetypes for Cloud Applications, sorry. It's, I would encourage you folks to read it. You can find it online. It's a fairly straightforward search. The authors are Googlers, but there's nothing Google specific about the paper. So it's a very generic cloud-based paper and really good information in there. I've read it a couple of times, so I definitely encourage doing so yourselves. Okay, so what are these archetypes that we are harping on? Very simply put, you should think of these archetypes as deploying your application in a zone, you'd call that a zonal archetype, or in a region, a regional archetype, across 2 or 3 regions, that's a multi-region archetype. And then if you're going across all regions across the world, you would call that a global application or a global archetype. Each has certain variants that are more descriptive in name. And we're not going to have time to cover all of these. We will pick a few. And given that this talk is centered on reliability, we will examine them more from an availability and reliability lens. Right? And what you'll see is these are effectively design patterns that optimize for a few things. They optimize along dimensions like availability, cost and complexity, latency, and at the end of the day, it's just a balance of trade between these dimensions. And really what you're trying to do here is you're trying to match your business requirements of your applications to one of these archetypes. Okay? Generally speaking, if it's a zonal archetype, you're deploying into a single zone. You may have a failover zone. So you can't expect very high availability. On the other hand, if you're deploying across multiple regions, you have your application now in multiple regions across multiple zones, so you can tolerate various kinds of failures, and therefore you can expect a much higher availability. Right? So that's the intuition behind these different design patterns. So let's dive in. The first one is what we call a single zone with failover zone. It's the most straightforward one to also understand. And if I get your attention to the picture on the right there, you basically have your application deployed in one zone, the primary zone. It's also a very simple application, just a front end, if you will, in this example with a database. You're keeping a read replica of your database that's not active in another zone. And when you have a failure, you fail over to the second zone. If you have deployed applications in the on-premises world, this will look somewhat familiar, where you have an application in data center 1, you have another data center not that far away, and then you use that data center for failover when something goes wrong, either to your application or to the physical data center itself. So what that also means is, when you are trying to do a on-prem to cloud migration, if you follow this design pattern, it's more of a lift and shift. You're not doing a whole lot of re-architecture. Therefore, cost and complexity also is on the low side. But because you're only deployed in a zone, you can't, again, expect a whole lot of, you can't have high availability expectations. 3 nines is roughly where you will tap out. Okay? So with that simple example to start, let's move to the next one. Now, this is single region. Now, just the picture alone will tell you that's a little bit more complicated. And what you're doing here is you're deploying your application across 3 different zones within that region. You can therefore tolerate a zone failure or even a multi-zone failure. Right? You can tolerate 2 zones failing because your application is deployed across all 3. In this example, you're using a little bit of a modern architecture. You have a front-end load balancer for your front ends. You have a back-end load balancer and then your back ends and a back-end data store. You have 3 copies of your data. One's active. The other 2 are replicas on standby. And if a zone fails, you're simply redirecting traffic through your load balancers to the other zones. And if your zone's back up and running, or your application in the zone is back up and running, then you're using all 3 zones to serve your application. Now, if you're doing a migration from the on-prem world, then there is some level of re-architecture that you'd have to do, because this is a little bit more of a scale-out architecture. And that also means from a best practices standpoint, you have to start thinking about things like auto-scaling your applications as load increases, or scaling down, or load shedding as load decreases, or if you have some sort of a problem with a portion of your application. The nice thing, though, is if you're using Google Cloud managed products, you tend to have constructs like these that help you out. So there's something called as MIGs, Managed Instance Groups. People who have worked on Google Cloud are probably familiar with this. It takes care of a lot of things like auto-scaling out or scaling in. When it comes to block storage, we have something called as regional persistent disk, which effectively creates 2 copies of your storage synchronously, so they're kept up to date between 2 zones within the region. So again, if a zone fails, you have a copy in another zone that would be up and running. So to single region, you can typically expect about 4 nines of availability. Okay, so at this point, let's actually walk through a little bit of an example. And what we're trying to do here is we're trying to derive a SLO. Right, so at the end of the day, you're going to be using a set of Google products and resources in Google Cloud, and then you have to think about, hey, at the application level, how do I derive or think about a SLO, service level objective? And in this example, we try to keep it somewhat simple. We have 3 components. You have the load balancer that's bringing in requests. Then you have your compute side. In this example, we're using GKE. And then, of course, you have your database. In this case, it's SQL. If you look at the product level SLAs that you get from each of these, the load balancer, the SLA is 4 nines. So under the covers, clearly, we are doing a bunch of things to make sure it's 4 nines. You're abstracted from it. So all you see is, a regional load balancer that has a fairly high SLA. And then the GKE clusters here are zonal clusters. So you have an SLA of about 2.5 nines. And then, of course, on the SQL side, if you're using managed SQL or Cloud SQL, you get 3.5 nines. Now, that's not good enough if you're trying to construct an application, let's just say, with 4 nines. So what you do is you start adding redundancy, right? So you deploy GKE, you deploy your application across multiple zones, as we saw in the archetype. So you're now deploying GKE across multiple zones. You're doing the same thing with SQL. Here we just used 2 copies of SQL. It could very well be 3. And as you're adding redundancy, of course, you're raising the availability, right? Intuitively, that makes sense. And the way you'd do that math, of course, it's a bit theoretical, but the way you do that math is 1 minus the error budget raised to the number of redundant copies that you have. So in this example with GKE, it's 1 minus the error budget is 0.005 raised to the power of 3 because you have 3 copies. You do the same thing for SQL, and then you get some numbers. Now, the fact of the matter is, those numbers are a bit theoretical. The reality is you will finally be bounded by something else within the region. Could be some dependency, or the fact that physical infrastructure can only give you so much availability within a single region, and that bound usually tends to be about 4 nines. So now what do you end up with? You have 3 components, each giving you about 4 nines. If you architect your overall application in such a way that they aren't fully dependent on each other when it comes to failure modes, then you can expect that your application itself can also achieve about 4 nines. So that's a way to just think about your application level SLA when you're using Google products, and Google products typically publish an SLA, and you probably have to add a redundancy in some cases to get to your target SLA, okay? So that was an example with single region. Now let's go and get a little bit more advanced, and now let's talk about a single region with a failover region. Now, as you can see in that picture, what are we doing here? We have taken the single region archetype, and we have said, hey, you know what? We need to also have something similar in another region, a failover region. So your application is, again, deployed across 3 zones in the region, same setup as before, but you have your data being replicated into a standby region. So you're probably doing async replication if your region is far away. And then when there's a failure, you're going to fail over into your standby region, and you're going to spin up your compute resources either just in time, or you might pre-provision. It all depends on what you're trying to optimize for. This is certainly a more complex archetype. Customers typically reserve this for the mission-critical applications rather than all of your applications. As you can see, the cost of this is going to be a bit on the higher side. Complexity is also going to be a bit on the higher side. And one thing that you really should take care of from a best practices standpoint is making sure that you are well aware of the health of your application through the stack. The reason for that is you don't want to fail over unnecessarily, because failing over to another region is going to be a high-cost activity, right? You are spinning up new resources. You're trying to make sure that your application comes up in the right order. You are moving your clients there. You're also operating on a copy of data that's probably 10, 15 minutes behind, right? So your RPO is in the order of 10, 15 minutes. So you want to make sure that you're really failing over when either your region goes down or your application within the region goes down, right? Another thing that you should think about is if your application is really large, taking up a lot of resources, is that you have capacity in the region that you're failing over into. So some capacity planning in advance is a good idea. One of the things that customers do is they pre-provision resources ahead of time, or they do frequent DR tests to make sure that when something bad happens, you have tested enough to know that you will fail over and things will all work. Okay, so that's single region with a failover region. Sometimes we call this a dual region architecture, right? Because you do have 2 regions. The last one is more of a true dual region architecture, where each region has an isolated stack. So again, you're taking your application, you're deploying it in 3 zones within a region, but you're doing exactly that in another region. And these are both active copies of your application. So you're serving clients from both regions. You have a load balancer, some sort of a DNS load balancer that's appropriately partitioning your traffic into the 2 different regions. And so what happens is if a region fails, you still have your other region that's serving traffic. And you can decide how you want to handle that situation. You can either redirect all your users from the failed region to this surviving region, or you can say, hey, you know what? I'll operate in degraded mode, and I'll only serve about 50% of my users appropriately, or I'll serve all of my users slowly, right? So it's up to you how you want to sort of handle that. Again, depends on your business goals. Clearly, this is a more expensive and more complex design, right? You have many copies of your application that's actively running, so you're actively, spending during that time. And it's certainly more complex because you have many moving parts and you have to make sure they're all well coordinated. So again, this is much like the previous one, this is something that you would reserve for your mission critical applications versus just every application that you have. Okay? So let's do a quick recap. So we discussed the concept of deployment archetypes. Simply put, it's just deployment architectures or deployment patterns. We discussed 4 of them. You can loosely classify them into a single region versus a dual region design. And you go higher up in availability, but you're trading off cost and complexity when you do so as you go from a single region to a dual region. And therefore, you must make sure that you're appropriately matching the archetype to your business goals. Okay? So this is the end of the theory bit to build a little bit of a foundation that we can now use with our real-world examples. And to talk through that, we will start with Cruise, and I'm going to hand over to Nitish.
Can you hear me? Okay, awesome. Okay, so we're from Cruise. Hopefully all of you have heard about us. We're a driverless car company based here in SF. But before I talk about our business application of these deployment archetypes, I'm going to just look at a summary here, right? So this is based off what Tim just talked about. What deployment archetype are we choosing and why? So immediately you'll see we have like a pretty high requirement of 5 nines of reliability. I'll talk about why a little bit later. We're using multiple regions. So it's a dual region, but it could also be 3 regions if we wanted to instead of 2. And we use regional GKE clusters as our basis in each of those regions. So even within a region, we're using regional services instead of zonal services. And then for our applications, we sort of have like 3 layers that our applications use. This is pretty standard. We have like a database layer for which we use multi-region Cloud Spanner. The great thing about Cloud Spanner is like multi-region out of the box. We have a messaging layer. I have a slide about that, talk about later. And then we have a custom load balancer that we've built to distribute traffic across our different regions. Okay, so about Cruise, even if you've not heard about us till now, like we've been in news a lot recently. All of you are in SF, which I think is fair to say is the driverless capital of the world, driverless car capital of the world. We are a self-driving car company headquartered here. We're building the world's most advanced self-driving cars, and these safely connect people to the places, things, and experiences they care about. Quick show of hands, how many of you have actually been in a self-driving car? Not that many. How many of you want to be in a self-driving car sometime soon? Many of you, right? So that gap is exactly what we're hard at work at Cruise right now to fulfill. We are rapidly expanding. We recently announced that we have gone to our 12th and 13th markets. It's very fast. I think we're testing now in Seattle and Washington, but we're going to be deploying services to Charlotte and Raleigh in North Carolina as well. So you can see where we are as a company, right? We have a product that works. It works in a few markets. Like right now we have public services in SF, Austin, and Phoenix. But very soon it's going to be across the US geographically, and it's going to be having multiple vehicles, right? Hundreds, thousands of vehicles, and many, many customers. So how do we take something that's built reliably in one place and sort of expand that across the country and expand that to a huge set of customers here? We have a unique product, obviously. The AVs themselves have pretty high availability requirements. Think of them as sort of like IoT devices, right? So they're IoT devices, but they're also like constantly on the move across these cities. They're also constantly on the move geographically spread, right? So you have AVs in Miami, as well as Austin, as well as LA. And these are constantly talking to our cloud backends, right? Like, where do I go next to pick up passenger? Should I go back to get charged into the garages? And our ride hail and delivery products that we're building on top of this technology will only be reliable if the AVs themselves are extremely reliable in terms of how they communicate with our cloud backends. Okay, next. So a couple years ago, we were in R&D mode, right? And when we were in R&D mode, we used a single GCP region. So I'm showing you the before, right? So that you can see our journey here. So when we were in R&D mode, we had a single region, a single regional GKE cluster, and we had sort of these monolithic services deployed in each of those zones. And all of them used Cloud SQL DBs, which is a regional product, and a GCP PubSub, which is also a regional product. We had load balancers that were pretty straightforward, just sending traffic across those zones within a single cluster. And the AV is talked only to a single region at this point. And yeah, this is sort of similar to what Tim showed you before in a single region architecture. We did not have like a failover or anything like that. Right? At this point, we were only focused on getting the technology itself to work. So like reliability was like the next step. Okay, so what comes next? So what comes next is, what comes next is 5 nines, right? I told you to talk about 5 nines. So 5 nines is like 26 seconds per month of downtime. It's very, very low. But think about the experience of a customer in a driverless vehicle being stuck for 26 seconds on the road in the middle of the night, right? It's a very uncomfortable experience compared to like not being able to access a website or an application for a minute or two, right? So we want to make sure that the experience our customers get is extremely reliable, and we know that we can only give that reliability with this level of cloud reliability itself. We are also in a nascent industry, and this is very important. It's a highly regulated nascent industry, right? So we have to also prove to the government, to our regulators, that this is a product that they can trust, that our customers can trust, and that is going to help us spread this product across the US. So the 5 nines here are not something we get easily, right? It's something we have to architect towards. Some of the examples that Tim showed you before like show a path to go from like 3 nines to 4 nines to 5 nines. And that's sort of like our journey here towards those 5 nines of reliability. The other thing I want you to note here is the applications here are consistently deployed across the different regions. It means that we have sort of minimized the amount of refactoring we have to do. I talked about the monolithic applications we had a little before. By deploying consistently across many regions, it's easy for our service developers to be like, hey, I have this one version of my microservice. I just want all the AVs everywhere to use it, right? And the architecture that we've built sort of allows them to do that. It makes it easier for them to deploy that code to these cloud backends. Okay, I want to focus in on the layers that we have as part of our architecture, and we'll dive into a couple of these layers a little later. If you look at each of these layers, each of them have to have finance reliability. So the cool thing is with the Spanner database layer, that's a multi-regional GCP service that gives us finance out of the box. So that's not a problem we had to solve. The next layer down is PubSub. So that's GCP PubSub, which is a regional service. So we had to architect finance reliability with that. And then we have the GKE clusters, which again are regional. And then we have the load balancers, which are regional. So you'll see that at the bottom, those are our AVs, right? And our AVs talk to a custom DNS load balancer, which directs it to different regions to use. And that is also like finance reliability, right? So layer by layer, if all those layers have finance reliability, we get finance reliability overall. I think he showed you the math slide as well, Tim, for that. Okay, so the two big things that we built here that we had to build in-house are the custom DNS load balancer and the GCP PubSub architecture. I'll talk about the traffic layer first. You'll see here that we have 2 regional clusters. These are like active, you could call them. And the AV has to be able to talk to them without like a failover, like a time taken for failover, right? So what happens here is we have a custom DNS load balancer that is constantly health checking our most critical services. You can see that, let's say, service A and service B are 2 critical services deployed to different clusters. They have their custom health checks with which the custom DNS load balancer can check for. And it'll only direct the AV to talk to a backend if it knows that's a healthy backend service in that region. The same thing is also applied for east-west traffic. So if you imagine that service A goes down in region US West 1, service B can actually talk to service A in US West 2 using the same load balancing logic. And when a health check fails, it's removed obviously from the DNS response. So no AV after that is going to be using that. A little more about this custom DNS load balancer. Some of our applications are very latency sensitive, right? Obviously, we need to have like command and control of these vehicles. They need to respond very quickly to them. So the DNS layer itself is configured with locality-based load balancing. It sort of means that the AVs themselves know which market they're operating in. And when they ask for a response, which cloud endpoint am I supposed to talk to, they get the one closest to them, assuming that's always healthy, right? It's only when the one closest to them is not healthy that it gets redirected somewhere else. So it's not like a random load balancing or like a fully distributed load balancing. It's definitely locality-based for those latency-sensitive applications. So this is, I think, the most useful slide to you. Honestly speaking, this is how we deployed a regional pub sub service and made it like multi-regional and got like 5 nines of reliability out of it. So we have an at least one messaging requirement out of our messaging service, but because GCP pub sub can only be deployed in a single region, we had to get 5 nines of reliability by deploying them in each region and having all your subscribers subscribe to all of them and all your publishers writing to all of them. So this is obviously more expensive, but it also means that if an entire region goes down, right, all our subscribers and all our publishers can still read from different regions immediately without like a loss of messages. Yeah, so this is how we got from like a thing that does not have like out of the box 5 nines of reliability to something that will give us 5 nines of reliability. Okay, I think I'm gonna need to hand off to Roman now. Thank you so much.
Hello, am I audible? Yeah, awesome. All right, so I'm going to talk a little bit about Egnyte. It's a slightly different product and architecture. And what I'll try and discover more of those archetypes that Tim talked about in his opening overview. Now, with Egnyte, we actually use several archetypes. I'll begin with one which kind of talks more about our core product. And in that case, we have an active region with a failover region kind of scenario. And in a moment, I'll explain a little bit why that is and kind of what powers that. Overall, we are using more or less standard GCP technologies, so we don't have too many custom components within that. But before I go much deeper, let me talk a little bit what Egnyte does, because unfortunately, I cannot make the same assumption that the previous speaker did. So Egnyte has pretty much 2 main pillars of functionality that we sell to our many customers, and we have 20,000 plus of these. One is what you would call file system in the cloud or advanced collaboration. So you have your company, they need to work on the same content, they need to work on mutual projects, they want to do it in a seamless way wherever they are, right? And it spans from the more basic use cases that you can readily imagine to pretty advanced ones that are tailored for a particular industry, such as construction. And then we have another pillar where people are administrators, in our case, they would want to reason about their data and understand that it's been processed in the right way, that there are no accidental or intentional incidents. So this is like a full analysis, whereas an administrator can come in and say, oh, this is something I need to worry about when it comes to data in my environment. So when we look at all of that, the main aspects that really would matter, and I'll come to them in a moment, is durability. Because if there is one thing that we cannot really afford is for anyone to lose their data. They entrust us with their data. It has always to be the right one. It has to be the current one. It cannot be lost. Again, to put things in contrast, availability matters a lot, because if as a customer you cannot access your data, in most cases you cannot function as a business. But that being said, if we are ever facing the very difficult choice of keep your data correct or keep it unavailable for a little bit, durability would trump, because durability will stay forever. Availability might come back in a few minutes, right? And I'm sure some of you have similar applications where you have those kind of long-term versus short-term concerns. Again, I'm not saying availability doesn't matter, and in a moment I'll go at length about how we are trying to reach a few nines there too. But we always have, as architects, think what matters the most, right? And what are the difficult choices that we have to construct when we look at a system. Now, one aspect I didn't put on the slide, but I'm sure everyone has it in the back of their mind, is cost. Because what we want to do is, of course, provide the right availability, but also manage our GCP bill so we can provide competitive pricing, remain profitable, all the things that all of us want to be at. And that kind of plays from a third angle into the architecture. So I kind of want to keep all of this in the back of our minds. Durability, availability, cost, when we review all of that. And of course, security matters without saying. I'm not going to talk a ton about that aspect, but I do want to highlight that we're a little bit like GCP in the fact that, yeah, we hold the data for our customers, but we can't access it. That's not our data, that's their data, right? So that also needs to be at the kernel of the thinking that the engineering has when it comes to multi-tenant systems like that. Now, what I want to do next is kind of take a vertical slice through the most basic use case. I don't want to throw my entire architecture or entire architecture at you, but kind of exemplify that thinking through one example. And this is the most straightforward one. Somebody comes in and wants to retrieve a file, retrieve some content. In that case, we first would go through a global load balancer. And that global load balancer would, first of all, tell where you are, because we have customers around the globe, and we are running multi-regions. But you are from birth as a customer, from the point you became a customer, you are being assigned somewhere. It could be US West, US East, Europe, but you are somewhere. And at the point your request comes in, we are already multi-easy. We decide, okay, your request lands at, say, zone B in US West. Okay, let's work with that assumption for a moment. And then we go through our API gateways, we go through our cache, we go through all of the optimizations that I put there, and for simplicity, I've even omitted like half of them. But the main point is, let's say the request came in and boom, availability zone goes off in the middle of that, or a particular service in that availability zone. It can happen, right? And you can say that's like a 3 nines kind of event. So the way we constructed that is by default, we stay within availability zone. But if something happens, we jump to the adjacent one. And one can ask, why don't you do that by default? Why don't you just, because they are close by, latency shouldn't be a big deal. But for us, costs, now I go back to that last principle I mentioned, because we deal with petabytes of data, we deal with terabytes of data that probably got downloaded since I got on the stage, in Egnyte's case. So we really have to manage our costs, and we don't want to do cross-availability zone traffic just because we can, right? We want to do it only if we have to. And that's part of this, how the system was architected. And of course, if availability zone goes entirely for a while, at that point we go and all of the requests will land on a given availability zone going forward, right? So now let's ask the question, what happens if an entire region goes down, right? That's probably the question that's front of mind. But in that case, we have, going back to the archetypes, active and a failover. If you remember Tim's overview, that was the third archetype that he covered. So we have this failover region where we constantly go and we provision our compute in there, we constantly replicate the data there, it's always current, but it's not serving requests. And I'll tell in a moment why, because that sounds like you have it, why don't you go the whole way, right? So I'll explain in a moment why we don't want to do that. But first, let's say if a region goes down, we go and we take a decision and we move to that read-only region right there and then. Now, why don't we want to have them live all the time? Now, I go back to that first principle I talked about, durability and data recency. Because now, many of you probably know what cap theorem is and how difficult it is to achieve at scale. Now, we want the data to be consistent. So let's say I'm here editing some file and somebody is there in the other part of the globe is editing in the same file, and they have different regions serving that, one going out. So you can imagine how many cases now we have to deal with not to lose any of our two modifications to that content. It's almost impossible, if not completely impossible. I don't remember the theory, but let's say if somebody manages to do that, they can command a ton of respect and money. So what we do, basically, we are saying, okay, we want to simplify that, active failover. And if we failover, we do first what's called the read-only failover. So you can access your data, but you cannot modify it yet because we still, if that region is not fully out and it's still doing some kind of semblance of life in it, we still might be in a tough spot. But if that outage is prolonged, we cannot tell our customers, hey, you can only read your data, you can modify it for some time. So at that point, it's okay, let's upgrade the failover to a primary. At that point, it's a one-way street. At that point, basically, that becomes the primary, and that one might become now the failover. And of course, it would involve some work. So that's kind of a pattern that I don't think is that unique to Egnyte. If you kind of think about it and you architect your systems, you worry about cost, you worry about availability. It's definitely worth considering in many scenarios. So at this point, I'll just quickly want to give one little counterexample, and then we'll pass to my colleagues for Q&A. So back in the beginning, I mentioned we've got two products, or not products, but let's say pillars. And I mentioned there was one admin facing where, as an administrator, you can look at the stance of your data. And there we actually have a slightly different archetype, because here the stakes are a little bit different. Of course, as an admin, you cannot fly blind, right? If suddenly a region went down, we cannot tell you, okay, for 2 days this thing will not be active. But that's different from saying nobody can collaborate in your company, right? That's a slightly different level of impact. So here we are running a single region. We don't have a failover region, but we can easily create one on demand, and the data is replicated. So unlike with that previous example where we can snap our fingers and get a failover within an hour, half an hour, whatever, here it might take maybe half a day. And again, that goes back to the principle where we're constantly trying to balance and see and do exactly the right amount of availability. Not more, not less, something that gets us to the right cost bracket.